The other part I talked about in class was that this is not the only potential energy around. We can talk about a few different things, and the one we're directly going to be talking about is the energy you get if you stretch or compress a spring or a rubber band. Because you yourself can know if you pull or stretch a band, there's energy in there. That's how you would launch a rubber band at somebody if you were going to do that, because you store energy in the band by stretching it out. And if you remove that force, that energy wants to do something, it wants to go somewhere, it wants to be used, and so it gets turned into kinetic energy. So it is a conservative force. You store energy in an object like that by stretching it or compressing it, and then you can use it if you remove the force that's doing that. So the potential energy for a spring, as we ended up deriving in class, is equal to 1/2 times K times x minus x0 squared. So what are these things? K is the spring constant, which will be dependent on the material, the spring, the rubber band, whatever it is that you're actually using that's being stretched or compressed. There will be a number like that between 100 newtons per meter and, say, 100,000 newtons per meter, depending on how flexible or how stiff your spring is. And this, x minus x0, is how much it's been stretched or compressed. If x0 is the length of the spring, if it's not stretched or compressed. So if your spring is nice and relaxed right here, then this would be its equilibrium position, or x0. If you stretch it or compress it, first let's compress it, then you've stored energy in the spring based on how much it's deviated from the initial equilibrium position. If you push it in further, you've got more energy stored than if you push it in only a little bit. The same thing happens if you stretch it out. What matters is the difference between its resting position and how much you've actually stretched it out. The further you pull it, the more energy is being stored in there. And so that is this x minus x0. You can simplify things and say that if you define x0 to be equal to 0, right here, then the PE is equal to 1/2 kx squared, where you get rid of that term if you define that to be at 0, which you are allowed to do. You don't have to do that, but you can certainly do that. This comes with a force, of course. So the force associated with this is equal to negative k times x minus x0. Again, it depends on the distance it's been stretched or compressed from the equilibrium point, from the place where the spring doesn't have any energy stored in it. So think about this for a second. If you are pushing a spring, or you are pulling a spring or pulling a rubber band, you feel a force going in the opposite direction back to where it was to start with, back to the original position before you messed with it, right? And the more you pull on it, or the more you push it, depending on if it's a spring, then the greater the force you feel. And you feel it in the opposite direction. So it depends on how much you stretch or compress it from the initial position, and you would feel it in the opposite direction of what you are doing to it. So the negative takes that into account. This would be the spring force, or a Hooke's law force. It's also called a restoring force because it wants to go back to that position. It turns out, just like with gravity, that the conservative work done by the spring force is equal to negative the change in potential energy of the spring. Which means that we get to rewrite our equation for work and energy to include the situation where springs are involved as well as gravity. So if we start off very initially, like we did before, that all the different types of work around added together will equal the change in kinetic energy. So now you have to look at all the different conservative works that could be done, and one we have due to gravity, and one we have due to the spring force. So WNC plus W spring plus W gravity is equal to delta KE. And through the derivations we did in class, we found out that WNC minus delta PE spring, let me rewrite this for a second. WS is equal to negative delta PE spring. WG is equal to negative delta PE gravity. So WNC plus negative delta PE spring plus negative delta PE gravity is equal to delta KE. So I want to put that over there, just like I did before. WNC is equal to delta KE plus delta PE spring plus delta PE gravity. So now we have any work done by non-conservative forces is equal to the change in kinetic energy plus the change in spring potential energy plus the change in gravitational potential energy. Let's write this in the specialized case so that we can analyze what this really means. If there's no friction, that's 0, right? So we have 0 is equal to delta KE plus delta PE S plus delta PE gravity if no friction. And this brings us to the same situation I mentioned at the very beginning of this recording, that the energy initial is equal to the energy final. Or that, well, let me write this out first. 0 is equal to 1/2 mvf squared minus 1/2 mvi squared plus 1/2 kxf squared minus 1/2 kxi squared plus mg y final minus mg y initial. And then rewriting this up here means that I can bring all the negative stuff to this side to make it positive and keep all the positive stuff on that side. So I have 1/2 mvi squared plus 1/2 kxi squared plus mgyi is equal to 1/2 mvf squared plus 1/2 kxf squared plus mgy final. Or energy initial is equal to energy final. Again, with the conservation of mechanical energy, but now we just have springs along with the force of gravity. So we have a spring force that can store energy, we have a gravitational force that can store energy, and we have the movement of the object, in which case the energy has been harnessed, being the kinetic energy. Okay, so these two things can contribute to giving kinetic energy to an object or taking it away. Okay, but conserving it. And we're going to be dealing with this idea more in the next class. But basically, this was about conservation of energy, and it was about adding in a different type of conservative work than we've already talked about, and seeing what that does for a different type of potential energy when we have both the spring potential energy and we have the gravitational potential energy.